This video tells the 4.6 billion year story of our star system, from its humble beginnings as cosmic dust to the dynasty of planets we inhabit today. We will explore how the laws of physics guided this incredible journey. Our story began 4.6 billion years ago in a giant molecular cloud, a vast, cold stellar nursery. This cloud contained raw materials, 98% hydrogen and helium, and 2% heavier stardust, formed in earlier stars. A nearby supernova shockwave triggered the collapse of the cloud fragment. Under its own gravity, the cloud contracted. Conservation of angular momentum caused it to spin faster and flatten into a protoplanetary disk, forming a dense, hot protostar at the center. For the next 500,000 years, the Sun existed as an unstable protostar, gathering mass from its parent cloud. A critical problem arose. The protostar would spin so fast that centrifugal force would tear it apart, known as the angular momentum problem. The protostars solved the spin problem using powerful magnetic fields and jets. These fields captured ionized gas and flung it outward, efficiently removing angular momentum. This process slowed the protostar's rotation, allowing more material to accrete onto it. The protoplanetary disk was the cradle of worlds. A critical boundary, the frost line, separated the system into two chemical regions. Inside the line, only rock and metal could condense. Outside, volatile ices provided vast amounts of building material. Planetary formation occurred through accretion in two ways. Inside the frost line, rare rocky materials merged to form the small terrestrial planets. Outside, abundant ices allowed protoplanets to grow much larger and capture vast amounts of gas, forming the gas giants. After 50 million years, the core of the protostar became hot and dense enough to initiate nuclear fusion, known as the proton-proton chain. This energy release balanced the inward pull of gravity, allowing the Sun to achieve hydrostatic equilibrium and enter its stable, main-sequence life. Around 4 billion years ago, the early solar system underwent a dramatic instability known as the Great Planetary Migration. In the NICE model, Jupiter and Saturn achieved a 2-to-1 orbital resonance. This destabilized the outer system, scattering icy bodies and shaping the outer reaches of the solar system. The migration event unleashed a period of intense, frequent impacts called the Late Heavy Bombardment. This destructive era was crucial, delivering water and other volatile compounds, the essential ingredients for life, to the inner planets. The disk eventually vanished due to photoevaporation. The Sun's intense radiation heated the gas in the disk, creating a powerful thermal wind that blew the remaining material away. This inside-out dispersal rapidly cleared the system of gas and dust. Following the tumultuous youth, the system settled into an age of stability. The planets achieved relatively circular and stable orbits, providing the conditions necessary for complex systems, including life on Earth, to evolve. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and swell into a red giant, increasing its luminosity by over 2,700 times. Mercury and Venus will be swallowed, and Earth will be incinerated. After the red giant phase, the Sun will expand one last time, gently puffing off its outer layers to create a planetary nebula. This peaceful dispersal enriches the interstellar medium with heavier elements, providing raw materials for the next generation of stars and planets. At the center of the nebula, the Sun's core will remain as an Earth-sized white dwarf, eventually cooling and fading into a black dwarf. After a quadrillion years, the system will cease to exist, its matter return to the cosmos, ready to begin the cycle anew.